Welcome to AI Paper Slop. Today we were looking at the paper Open-MOPD, which is Diagnosing and Fixing Capability Imbalance in Multi-Teacher On-Policy Distillation. And here is the core problem for anyone building models right now. Multi-teacher on-policy distillation, or MOPD, it's supposed to be the holy grail, right?
Right.
For combining multiple domain specialist models like your math expert, your code expert, and your chat model into one single generalist student using token-level reward supervision. But standard MOPD is currently failing.
Oh, completely.
Yeah, it only recovers about 35.6% of the performance you would get if you just ran separate specialist models in production. And this paper definitively proves that the bottleneck is not teacher conflict.
Right, which is huge.
Yeah. The teachers aren't disagreeing on tokens. The actual bottleneck is this catastrophic misallocation of the optimization budget. Concise tasks, like instruction following, are literally being starved of gradient tokens compared to long chain math and code tasks. Furthermore, varying domain convergence rates and reward staleness across PPO mini-batches completely distort the training signal. So the fix introduced here is a framework called Open-MOPD. It implements three mechanisms: token share balancing, gap-aware dynamic budget allocation, and student reward refresh.
Right.
And together these restore cross-domain balance and elevate performance recovery from that 35.6% to an impressive 83.4%.
Which is, that capability integration gap has been one of the most frustrating pain points for ML engineers working on post-training right now.
Oh, absolutely.
Because you have these brilliant specialist models, right? But deploying three separate huge models to handle user queries is just a computational and financial nightmare.
Yeah, keeping a math model, a code model, and a general chat model and GPU memory all at once just isn't viable for most applications. Which is the entire appeal of MOPD in the first place. You route your training prompts to the respective domain experts. The student model generates a response, and then those expert teachers look at the student's trajectory and provide this dense, per token reward supervision.
Right. You are attempting to basically bake three massive brains into one smaller, efficient brain.
Exactly. But it hasn't been working.
No, it hasn't. And to figure out why that baking process historically results in such severe capability degradation, the researchers behind this paper realized they needed a perfectly controlled environment. Like, if you want to study integration failure, you have to completely eliminate routing failure.
Oh, that makes sense.
So they set up an Oracle router based on ground truth domain labels.
So there's zero ambiguity there.
Zero.
If a prompt is a math question, the Oracle router ensures it goes exclusively to the math teacher.
Exactly. Because a standard reward model router might accidentally send a tricky Python logic puzzle to the math teacher instead of the code teacher.
Right, which would completely pollute the training signal.
Yeah, exactly. By using the Oracle, we know with absolute certainty that any failure to learn is happening inside the distillation algorithm itself. It's not a data routing issue.
Okay, so that isolation is critical. And the benchmark evaluated three distinct domains, right?
Right. So for math, they used OpenR1 Math. For code, they used OCR50K. And for instruction following, which we'll just call IF for now, they used instruction Nimatron.
Got it.
And they established a theoretical ceiling for this setup, which they call RouteOPD. That ceiling represents the score you get if you just, cheat and evaluate using the three separate specialized models.
Right, the ideal scenario.
Exactly. And the ceiling score is over 31.5.
But the baseline reality for standard multi-teacher distillation is pretty grim. Like, the naive MOPD setup barely breaks 28 points.
Yeah, it's rough.
And the penalty isn't distributed evenly across the domains either. Instruction following tasks just fall off a cliff.
Yeah.
The IF domain drops more than 6 points below its reference ceiling.
Yeah.
Which is, 3.3 times worse than the degradation seen in the math domain? The IF tasks also plateau much earlier in the training process than anything else.
They really do.
But before we break down the mechanics of why IF suffers so badly, we should look at the model they used to test this. Because they used small m3 3B base.
Right.
Why rely on a 3 billion parameter model for this? Like, a 1.7B parameter model would be so much cheaper to run experiments on, wouldn't it?
It would be, but the smaller model actually failed a fundamental prerequisite for this kind of research.
Oh, really?
Yeah. They initially tested Qwen3 1.7b, but found that between 69% and 80% of its reasoning trajectories truncated before it ever reached a final answer.
Oh, wow. Meaning the base model just didn't have the intrinsic capacity to hold the context or, discover the solution within the length limit.
Exactly. And if the model cuts off before finishing the thought, the training signal is inherently corrupted.
Right, of course.
You can no longer attribute a training failure to your multi-teacher distillation algorithm. The model simply lacks the architectural headroom to solve the problem in the first place.
Right.
So a 1.7b model introduces a massive confounding variable.
Okay, that makes total sense. That rules out the tiny models. But on the other end, why not jump to a 7B model? Like, Quen 2.57b is incredibly capable, and it handles long horizon reasoning beautifully.
It does. The 7B models solve the truncation issue completely, but they introduce a severe compute bottleneck.
Ah.
Yeah, the explicit goal of this research was to provide an open-source, rigorously reproducible recipe that an academic lab could actually run on a standard 8x A100 80GB node.
Okay, so making it accessible.
Right. Diagnosing these complex integration failures requires running endless ablation ladders. You have to tweak the loss function, change the batching, adjust the reward parameters.
Over and over again.
Exactly. Run the entire end-to-end multi-teacher RL pipeline repeatedly. Doing that at the 7B scale is just financially impossible for most teams outside of major corporate labs.
Yeah, that makes sense.
So small m3, 3B hits the perfect Goldilocks zone. It closes its reasoning trajectories, providing a clean signal without bankrupting the research budget.
Okay, so we have our 3B student failing to learn from 3 specialized teachers, and the instruction following capabilities are taking the heaviest hit by far. The most intuitive assumption, and honestly the one that usually dominates the conversation in these engineering circles, is that the teachers are simply giving conflicting advice.
Right, the teacher conflict hypothesis.
Exactly. Like, if the math teacher strongly prefers a specific syntactic token and the IF teacher penalizes it, that creates a catastrophic gradient conflict. The student basically freezes because it's being pulled in opposite directions.
Yeah, and it sounds perfectly logical, right?
Yeah.
These teachers share formatting words, connectives, and basic reasoning templates. But the researchers didn't just accept that assumption, they built a metric to explicitly measure it.
Okay.
They tracked the maximum difference in log probabilities among the 3 teachers for any given token generated by the student.
And they measured this spread in nats, right?
Yeah.
Which is a unit of information entropy based on natural logarithms. So if the spread is high, it means one teacher is extremely confident a token should be there, and another teacher is extremely confident it shouldn't.
Right.
So what did the actual telemetry show?
The telemetry completely dismantled the teacher conflict hypothesis.
Really?
Yeah. The mean spread across the entire training run was only 0.126 nats.
Wait, 0.126?
Yeah. To put that in perspective, a serious conflict would register at 1 nat or higher.
Oh, wow.
They found that only 0.62% of all tokens generated showed a strong conflict.
Less than 1%.
Exactly. The vast majority of the time, the teachers are fundamentally in agreement about the basic structure of the language.
Okay, but even at less than 1%, you could argue those specific high conflict tokens are causing outsized damage to the loss landscape.
You could, yeah.
So the researchers attempted to intervene. They built a conflict mask where they dynamically dropped the top 1%, 5%, or 20% of the highest conflict tokens directly from the loss function.
Right.
They essentially told the student, if your teachers strongly disagree on a word, just ignore them and don't update your weights for that specific word.
Yep.
And they also tried a consensus target approach, where they averaged the log probabilities of the 3 teachers whenever they disagreed.
And this is where it gets interesting because both of those interventions degraded the model's performance even further.
Really?
Yeah, the total score dropped by up to 0.83 points when they manipulated those high conflict tokens.
This is where we really need to rethink our assumptions about noise versus signal.
Right.
Because if I have 3 mentors giving me advice on a project, and they vehemently disagree on one specific detail, my instinct is to throw that detail out and focus on the broad strokes where they align.
Right, that's human nature.
Yeah. So why does doing that mathematically hurt the model here?
Well, in the context of multi-domain distillation, a high conflict token isn't noise. It's often the most critical piece of domain-specific nuance. Imagine a scenario where the student is formatting a response. The math teacher might heavily prioritize a specific latex token to structure an equation, right?
Right.
While the code teacher heavily penalizes that token because it completely breaks Python syntax.
Oh, I see.
That sharp disagreement is exactly the signal the student needs to learn the boundary between math formatting and code formatting.
Ah.
So by masking those tokens out or blending them into a diluted average, you are actively destroying the boundaries between the domains. You teach the model this bland, middle-of-the-road syntax that is basically slightly wrong for every use case.
Oh, wow. That is fascinating.
Yeah.
Okay, so teacher conflict is a total red herring.
Yeah.
The teachers aren't fighting. The plumbing of the optimization objective is just broken,
Exactly.
which points us directly to the real culprit behind the integration gap, which is the optimization budget.
Right. The mechanics of how on-policy distillation aggregates loss inherently skew who gets the resources to update the model weights. The paper identifies 3 specific mechanical failures happening under the hood. And the first one is straightforward: token imbalance.
Because standard on-policy distillation aggregates loss across individual tokens, not across prompts or entire responses.
Exactly. And look at the structural reality of the training data. A robust reasoning trajectory for a complex math proof, or like a coding problem, averages about 10,500 tokens per response.
Okay.
But an instruction-following response like writing a quick email or summarizing a paragraph that averages just 409 tokens,
Right.
that is a 25-fold difference in sequence length.
So the data sampling might be perfectly fair, right? It can pull IF prompts so they make up over 20% of the batch.
Right.
But because the resulting responses are so incredibly short,
Yeah.
those IF prompts only account for 0.99% of the actual gradient tokens being passed into the loss function.
Yeah.
The IF signal just gets completely drowned out by the sheer volume of math and code tokens.
It is a massive structural disadvantage. The domains that require verbosity naturally monopolize the optimization process.
This reminds me of trying to allocate a corporate budget. Imagine distributing funds to different departments, not based on their strategic importance, but purely based on how many words they submitted in their annual report.
Oh, that's a perfect analogy. Yeah.
Like, the legal team, representing our math and code domains, writes a 10,000-word manifesto detailing every single case, so they get all the capital.
Right.
But the graphic design team, representing our IF domain, submits a highly effective one-page visual summary. Because it's short, they get less than 1% of the budget and the department starves.
Exactly.
So the naive engineering solution would just be to ask the graphic design team for 30 pages.
Right.
Like, why don't we just heavily oversample the IF prompts in the data mixture until the token counts actually balance out?
Well, you can't, because the math on oversampling becomes physically impossible within the constraints of GPU memory.
Oh.
To elevate the IF domain so it occupies just 1/3 of the total token budget, you would need to multiply the number of IF prompts in every single batch by 33.6 times.
You would just flood the batch with short, chatty prompts.
Exactly. And in doing so, you would squeeze the math and code prompts completely out of the context window.
Oh, I see.
Long-chain reasoning domains require massive batch context to stabilize their gradients. If you pack the batch with 33 times more IF prompts, you barely have room left for a single complex math problem.
Right.
You solve the IF starvation by destroying the supervision environment for reasoning.
Yeah, that completely rules out oversampling.
Right.
So token imbalance is our first massive failure. The second failure the paper highlights is what they call unequal shrinkage and drift.
Right. The effective update budget allocated to a specific domain isn't just a product of token count. It also heavily depends on the reward magnitude.
Right.
And the reward magnitude is the mathematical gap between the teacher's target policy and the student's current policy.
Okay.
Early in the training process, the student is terrible at instruction following compared to the dedicated IF teacher. So the IF reward magnitude is about 4.9 times larger than the math reward magnitude.
Because the student has a lot more ground to make up in that domain early on.
Exactly. But these domains do not learn at the same speed.
Right. They converge at wildly varying rates.
Yeah. As the student gets better at IF, that gap shrinks rapidly. And this introduces a dangerous temptation for engineers looking at the loss function.
Of the inverse normalization thing.
Exactly. A common hack is to use inverse normalization. The logic basically goes, if a domain's reward is getting too small because it's converging, let's artificially inflate its weight in the loss function to keep the gradients flowing and prop it up.
You try to forcefully balance the scales.
Right.
But the paper demonstrates that inverse normalization triggers a literal training collapse. Walk us through the mechanics of why that happens.
Inverse normalization basically creates a catastrophic positive feedback loop.
Okay.
A domain begins to learn, so its reward magnitude naturally decreases. The inverse normalization algorithm detects a small reward and applies a massive multiplier to that domain's weight. But because it now has a massive weight, the model optimizes that domain even faster in the next step.
Oh, no.
Which means the reward shrinks even further, which triggers an even larger multiplier.
It just spirals out of control.
Exactly. The paper's telemetry shows the IF weight skyrocketing exponentially until the gradients explode and the entire training run crashes at exactly step 74.
Step 74. Wow.
Yeah.
You are mathematically incentivizing the model to aggressively optimize for the things it already knows the answers to.
Yes.
It's a completely inverted incentive structure. So we have token imbalance starving domains based on length and unequal drift destroying domains based on convergence speed.
Yep.
The third major mechanical failure is reward staleness.
And staleness is a direct byproduct of how we try to save compute during reinforcement learning.
Right.
Generating responses from these models is incredibly expensive. So training pipelines will generate a single rollout batch of responses and then reuse that exact same batch for a set number of inner PPO updates. We call that number K. So let's say K equals 4. You do the expensive generation once, and then you run 4 consecutive gradient updates on the student model using that data.
But wait, the student's neural weights are changing after update 1, update 2, and update 3.
Right.
By the time you get to that 4th update, the student is fundamentally a different model than the one that originally generated the rollout batch.
Exactly. And the researchers quantified exactly how different. By the 4th update, the student policy has drifted so far that the KL divergence hits 0.059.
Wow.
And more alarmingly, 85.8% of the tokens are being actively clipped by the PPO objective function because the current student's probabilities have deviated too drastically from the original rollout probabilities.
So PPO is throwing out like 85% of the data just to protect the model from volatile updates.
Yeah, exactly.
Yet standard MOPDs is still looking at the student probabilities from the very first rollout to calculate the dense reward for that 4th update.
It is.
It's like it's grading the student's current exam using an answer key based on the student's knowledge state from 3 updates ago.
Yeah.
The reward signal becomes completely detached from the student's actual current policy.
Exactly. So those are the 3 structural failures of standard multi-domain distillation. The optimization budget is broken by sequence length, it's distorted by convergence rates, and it's corrupted by compute-saving staleness.
Which brings us to the architecture of Open-MOPD and how it systematically eliminates these 3 failures.
Right.
The first intervention is token share balancing, which directly targets the sequence length disparity.
Yes. So instead of allowing sequence length to dictate the gradient budget, they enforce a hard target budget. They mandate that math, code, and IF each get precisely 1/3 of the optimization budget, regardless of how many tokens they actually produce.
Okay.
The system dynamically scales the loss at the individual token level to enforce that target.
Let's look at the math on that for the IF domain. Because its responses are so short, only 409 tokens compared to 10,000 for math. What does that scaling factor actually look like in practice?
Well, to hit its 1/3 target, every single IF token gets its gradient amplified by roughly 48 times.
Wait, 48 times?
I said 48 times.
Multiplying a gradient by 48 sounds incredibly destabilizing. Like, usually large multipliers lead to the exploding gradients we just talked about with inverse normalization. Why is this safe?
It's safe because it's fundamentally different from inverse normalization.
How so?
It's not chasing a shrinking reward gap, right? It's simply correcting for a static disparity in sequence length. It normalizes the token's impact relative to the batch, and the empirical results confirm its stability. This single mechanism yields a plus 1.17 point gain in overall performance.
Wow.
Yeah, effectively rescuing the IF domain from starvation without needing to oversample prompts.
Okay, so that solves the token volume issue. The second intervention, gap-following allocation, addresses the drift and the catastrophic collapse caused by inverse normalization.
Right. Gap-following allocation completely reverses the broken logic of inverse normalization.
Okay.
Instead of inflating weights as a domain converges, it dynamically directs the optimization budget toward the domains that have the largest remaining teacher-student gap.
Ah, okay. So if a domain is struggling and the student is far away from the teacher's target, it gets more budget.
Yes.
But when it starts mastering the domain, closing the gap, its budget automatically drops.
Exactly. It treats a large reward magnitude as a signal that the capability has not yet been distilled.
Makes sense.
And to prevent the algorithm from overcorrecting, they clip this allocation factor between 0.05 and 20.
Okay.
The telemetry from the experiment shows this working beautifully. The code domain had a massive amount of capability left to learn right.
Right.
And as the training progressed, gap-following allocation organically ramped code up until it consumed 87.6% of the budget.
Oh, wow.
Yeah. Meanwhile, the IF domain learned quickly, converged, and safely dropped down to about 17% of the budget.
So it's entirely self-correcting. It shifts resources in real time based on actual learning needs rather than arbitrary schedules.
Exactly.
The third and final intervention is reward refresh, which targets the staleness of those K inner PPO updates. Now, anytime someone in ML suggests fixing staleness by getting fresh numbers, my immediate thought is a massive compute penalty.
Right, right.
Because getting fresh rewards usually means running another forward pass of your models.
Yeah.
How do they implement a refresh without destroying their throughput?
Well, the dense reward calculation relies on two components, right? The teacher's log probabilities and the student's log probabilities.
Right.
The brilliant engineering insight here leverages the fact that the teacher models are entirely frozen. Their policy never changes during training.
Oh, okay.
So during the initial pre-fill, you calculate the teacher log probs once and cache them. You never need to run a teacher forward pass again for that entire batch.
Right, so caching the frozen teacher is standard. But the student is updating. You still need the student's fresh log probs for update 2, 3, and 4 to calculate an accurate dense reward.
You do, but PPO is an actor-critic algorithm.
Yes.
Before each of those K inner updates, PPO is already required to do a forward pass on the actor, which is the student model, to get the action probabilities needed for the standard PPO update equation.
Oh.
Yeah. The researchers simply piggybacked on that mandatory compute. They pull the fresh student log probs generated from that existing PPO forward pass, combine them with the cached teacher log probs, and recompute the dense reward perfectly.
They update the dense reward using a forward pass they were already paying for anyway.
Exactly.
That is incredibly elegant.
It's amazing. It completely eliminates the staleness problem. The reward signal is perfectly synchronized with the student's drifting policy at every single inner update.
Right.
The compute overhead is practically non-existent. It takes only about 2.2% of a step time, and it yields a solid plus 0.81 point bump in performance at K4.
That's fantastic. Let's zoom out and look at the cumulative impact of these three mechanisms. When you combine token share balancing to fix volume, gap following allocation to fix drift, and reward refresh to fix staleness, what is the final verdict on the Open-MOPD framework?
The results fundamentally change the viability of multi-domain distillation. The total score of the student model jumps to 31.24.
Nice.
And compare that to the naive baseline of 28.05, right? And remember that the absolute Oracle ceiling using 3 distinct models was 31.55.
So the integration gap, the penalty you inherently pay for cramming 3 distinct models into one, is crushed from 3.4 points down to just 0.31 points.
Exactly. The total headroom recovery skyrockets from 35.6% to 83.4%.
Wow.
They solved the capability degradation problem at the mechanical level of the loss function. And crucially, they have fully open sourced the entire end-to-end recipe, the resulting trajectories, and the evaluation suites for the community.
So for the ML engineers listening to this, the practical takeaway is immediate. When your multi-domain model is failing to learn a specific capability during post-training, your first instinct should no longer be to overhaul your data mixture or, assume your teachers are hopelessly conflicting.
Right.
You need to audit your gradient token distribution. Your model might literally just be starving a highly concise domain of optimization budget because the sequence links are structurally imbalanced.
Exactly. We have a tendency to treat RL pipelines as opaque systems where injecting more data is basically the only lever we have.
Yeah.
But this research proves that if the underlying token economics of your optimization objective are broken, no amount of data scaling or perfect routing will fix it. You have to balance the mathematical ledger first.
It all comes down to the token economics, which leads me to a final thought for everyone building these pipelines to consider. Open-MOPD clearly proves that we can distill completely distinct specialist teachers into one coherent student by meticulously managing the optimization budget, specifically by using gap-aware allocation to steer the budget toward whatever domain is struggling the most.
Right.
But this framework is currently applied to supervised static teachers. Could this exact same mathematical mechanism be reverse engineered to dynamically balance unsupervised RL environments?
Oh, applying gap-aware budget allocation to open-ended self-play.
Exactly. One of the biggest problems in unsupervised self-play is that the model will reward hack, right?
Oh, constant.
You will find a specific, easily solvable subdomain, exploit it, and ignore the harder, more complex environments. But if we can perfectly balance reward tokens based on the remaining capability gap, perhaps the next frontier is using these open MOPD mechanics to automatically detect when a model is reward hacking a simple domain. The moment the gap closes and the domain becomes too easy, the allocation algorithm dynamically defunds it, forcing the model to reallocate its exploration budget toward the harder domains it's avoiding.
You would be using the token economics not just to balance knowledge, but to automatically steer exploration in an open environment.
Exactly. Something to mull over while you're profiling your next training run. Go read the open source code for Open-MOPD. The engineering is highly worth your time. Thanks for joining us, and check back soon for our next paper breakdown on AI paper slop.